Okay. Hi, hello everyone. I'm happy to be here to speak about HPC technologies and a lot about advancements that we have in high-performance computing and advantages that we have. I want this session to be interactive, so if you have any questions, don't be shy. Just feel free to raise your hand, and we can take it more interactively and take questions. And if people have something important to say, just go ahead and feel free. So, to begin with, the heart of the high-performance computing system is the interconnect. So we're seeing a lot of trends happening in the industry where different CPU types are coming up, different accelerators, GPU, FPGA, you just name it, everything comes together, and people are building homogeneous and heterogeneous systems. And at the heart of it is the interconnect, where we want to make it as efficient as possible, make it smart, so that you can really scale and build every single block and element and optimize it so that it really scales and provides the overall performance that you need. So on the CPU front, we see the x86, we see the Power CPU coming in, we see the ARM CPU coming in. We have different types of GPU that significantly accelerate the performance, and we're seeing FPGA coming in more and more to accelerate performance by writing dynamic code that runs on the FPGA as well. So all of that for compute and for storage, scalability, the network is in the heart of it. So in terms of feeds and speed, we're in a very new era. We're in the era of 100 gig now. So you can see on the track record for Mellanox, we've been executing for many years. I'll introduce now the 100 gigabit per second era with all the chipset for it. We can see that since 2003, we have the first huge supercomputing at Virginia Tech, and we've been executing. And the next systems that are on the roadmap are the Coral systems, the Summit and the Sierra systems, moving towards an exascale computing. So the future is here, and 100 gigabit per second is here and is shipping now, and we have all the building blocks to enable the 100 gigabit per second. So I'm going to introduce each one of the pieces there, but at a very high level, you can take a look and see that there is the host channel adapter for 100 gigabit per second. That's ConnectX-4. There is the switch for 100 gigabit InfiniBand, which is switch IB. And there is LinkX, which is the 100 gigabit per second cabling solution. So ConnectX-4 is the first EDR adapter. It's very high performance. It's ultra low latency. It's less than 0.7 microsecond in latency. It has superior message rate even compared to previous generation. It can actually get to 150 million messages per second. And it supports all the speed bumps up to EDR. So all the backward compatible speeds are available also in ConnectX-4. Switch IB is a 36-port EDR switch. It supports 100 gigabit per second port, and we heavily optimize the latency of this device. So compared to the previous generation, this latency is amazingly low. It's sub 90 nanosecond latency per hop. And the overall throughput is a little bit more than 7 terabit per second. And on the LinkX, we offer the different cabling technology. We offer copper cables, we offer optical cables, and we offer silicon photonics. So let's start from the cabling side. So cabling, I think they're so popular, and you cannot do anything without the cabling solution. And when you put the cables, they have to be well tested so that you put them and forget all about them. And they're very challenging to deliver, especially when we're doing 100 gigabit per second and also always looking at the next generation to come. So those cabling solution for EDR, we offer copper cables and active optical cables based on two technologies. The first technology is VCSELs, which is the technology everybody is using today for FDR and now for EDR. And also the silicon photonics is coming in, and people will be able to use silicon photonic active cables now, and the silicon photonic technology will also grow into the future to enable even faster speeds than the EDR. So copper technology is very important, and what we did for EDR is we invested a lot in being able to drive longer reach copper. So basically we demonstrated in supercomputing, we're demonstrating copper cables running up to 8 meters of cable. So those cabling are very important because you can use them inside the rack, and when you get into 8 meters, you can even use them to connect adjacent racks. And I think this is a very important saving in the economy of building an HPC cluster, because you can save, first of all, on the CapEx when you're building the cluster. Those cables, those passive copper cables are always cheaper, and you can also save on the power because they don't consume any additional power. So in those examples, you can look at a medium-sized cluster of 5,000 nodes, or medium or large cluster. The CapEx saving from just the copper cables versus optical cables is about $2 million. And definitely on the power saving, you can even save on the operational expenses a few thousands or tens of thousands of dollars every year for managing this, for maintaining that cluster. So that's one of the most important things in the cabling technology, the ability to drive longer copper-rich cables for EDR. So now let's move to, yeah, go ahead.
Quick question in connector, is it still QSFP?
Yeah, the form factor for 100 gig is QSFP, so the cable pretty much look at the familiar form factor that you're used to, but you obviously need cables that run to the better quality and so on. But the form factor remains QSFP cables.
Question.
Yes?
On your site, there are cables only up to 2 meters. Will you publish this as well?
Yeah, we can talk about it later, but yeah, all the cables we will offer different sizes and we'll publish them on our site. We can follow up on this later. Okay, Kinetics 4. So Kinetics 4 architecture is based on the Connect IB architecture, and that's the first generation of EDR adapter. So what we basically did is we take the Connect IB adapter and enhance that with extra features. First of all, getting to EDR space, but adding more and more features, including optimization of message rate and so on. One big thing that was added into the Kinetics 4 is the support for Ethernet as well. So unlike Connect IB, the Kinetics 4 can speak both InfiniBand and Ethernet. Both of them can reach up to the 100 gig speeds. It's a by 16 PCI Express adapter. Bandwidth is overall 100 gigabit per second. That's maxing out the overall I/O performance available by the server. So that's pretty much maxes out by 16 PCI Express Gen 3. The latency is less than 700 nanosecond, and it runs 150 million messages per second. And I'll show you some measurements that we did in the lab. In addition, we have more features embedded into the Kinetics 4. It supports the open power CAPI technology. So that's one extension to the PCI Express semantics that can go together with the power CPU. We have support for the core direct technology, for the GPU direct technology. We have a dynamically connected transport that is further extending what we had in Connect IB. And we had offloads for Ethernet and IP over IB in order to optimize vanilla networking with checksum offload, receive side scaling, large and offload, and so on. So those are actual numbers. Those are very preliminary numbers, but those are numbers that we measured in the lab for the Kinetics 4, and those numbers are really amazing. So you can see actually hitting 100 gigabit per second bandwidth on the EDR links. You can see that even the bidirectional bandwidth, we managed to almost max out the two directions, getting to 195 gigabit per second of bidirectional bandwidth. The latency is actually even better, and it's 0.61 microsecond, very high message rate, 149.5 million messages per second, and actually taking that above the verbs and measuring that over the MPI, so the bidirectional throughput is actually 193 gigabit per second. So those are really impressive numbers that we're seeing with Kinetics 4 in the lab. And this slide basically shows over time the different generation of devices that we have and the message rate that you can see. The x-axis actually shows the number of cores that are running or the number of threads that are running in the CPU. Basically, you can see the black graph here shows the Kinetics 3 performance that is actually maxing out before 40 million messages per second. And if you look at ConnectIB actually maxes a little bit above 100 million messages per second. And if you look at Kinetics 4, then Kinetics 4 further extend that and maxes out at 150 million messages per second. This is a very important item for scalability because when the cluster grow, you usually need to pump smaller messages and you have to move more and more of them in a unit of time. So moving to the switch. So switch AB is there also in production. It's a 36-port switch. It's a 7th generation InfiniBand switch. That's an InfiniBand only switch. One of the key characteristics that we fully optimize there in the switch is the latency. So we keep a very, very low latency per hop. That's a 90 nanosecond latency per hop for that switch. That's a very important saving for that's a very important characteristic for scaling in HPC, and this is heavily optimized compared to the previous generation. The throughput is 7 terabits per second, and it has capability to run InfiniBand routing as well as adaptive routing. So if you basically look at the agenda, the next item that I have is to go a little bit more deeper dive into the adaptive routing, so I'll cover that as part of the switch. So in the switch system, we made also several improvements compared to the FDR switch system that we have today. So first of all, we have the offering of x86 CPU. That's a stronger CPU to manage the system for the managed systems. Basically, you can have better user experience from it, as well as you can run some code inside a VM that runs on a switch, so it supports the virtualization technology. So you can take advantage of it. We're having more and more power-friendly features, so the system is Energy Starts certified, as well as 80 Gold Plus for the power supplies. And all the ports support 3.5 watt so that you can run longer reach cables and have a little bit more power there. On the pizza boxes, we improved the fan drawers. We have more 2 power supplies out of the box. We have DC power supplies also available, and battery backed up unit as well, and improved the rail kit. On the modular systems, we basically introduced a dual leaf design that basically has 2 chips in it, and we have N+N power supplies, and other improvements in the modular design and power supplies as well. So comparing 36-port ASIC to other ASICs from different vendors, so you may ask yourself, what's the difference? So what I can tell you is that there is some high-level analysis here of latency, but obviously there are more characteristics. But even if you look down at the latency, as I mentioned, the latency in switch IB was fully optimized. So we're talking about 90 nanosecond for a single hop. So if you look at cluster size of 32 nodes, you're talking about 90 nanosecond between different servers. If you're building a fat tree, then the next bump will be 3 hops, and the further next bump will be 5 hops. So you can see the latency here calculated by this formula. If you look at other switches, they have not optimized fully the latency. And overall, we're seeing about 20% lower network latency in the Mellanox switch IB performance because of that single switch optimization latency. So that chart is mainly for fat tree, but we can do other calculation, other topology. Obviously, if a single hop is faster, then the entire connectivity will be faster, regardless of the topology. So let's talk about adaptive routing. So I want to introduce to you a little bit about the concept of adaptive routing, and I'm going to take it a little bit step by step. So the way routing works today, and that's the regular InfiniBand, the way InfiniBand switches and InfiniBand subnet manager, the OpenSM is configuring the network according to the InfiniBand spec, is based on linear forwarding tables. Basically, what we do today in a regular configuration is that every port in every adapter gets its own local identifier, or the way we pronounce it, lid. So this port has lid number 1, and this port has lid number 2, 3, 4, 5, and this one is 8. And even switch devices gets their lid assigned, so this switch is number 6 and number 7. And this assignment is being done by the subnet manager. So the next step is to program the routing tables, and basically each switch element has a linear forwarding table. Basically it's a linear table, every row represents a local identifier, and when you get into a row you pick up the port, and that's where the packet will go. So for example, if you look at those two flows, the red flow and the green flow, the red flow will go into that switch. It is destined to lead number 2, so it will go through that table. Lead number 2 goes to port number 2. It will exit from this port, and then it will go to the other switch. And here it will be destined to lead number 2, go through port number 1, and the packet will arrive to the destination. Similarly, that one works for the green flow. And basically, 3 and 2, those are the two output ports in the linear forwarding table, and that's how pretty much it works. So what's good about that is it's very fast implementation, because the only thing you do in the ASIC is to look up it through a linear table. It's very fast, very efficient. It's a low-cost mechanism, and those are the things that really improve the latency for the solution. And it's also very simple to compute. So that's how things works today. So if we go a little bit and explain blockiness of a fabric, then there are a few characteristics that were defined by Klaus. I'm specifically looking now into Klaus networks or fat tree networks. So basically there are a few levels of non-blocking. The first level of non-blocking is a fully non-blocking. This is where every permutation of pairs that you kind of randomize, you can actually run flows across them without creating any network contention. The second level of blockiness is strictly non-blocking. This is where, let's say that you're randomizing flows, but you're adding them one by one. You don't know a priori all the flows that you're planning to move, so you add more and more flows. So when you're strictly non-blocking, you can always add more flows, and they will not block. You can change the routing only for new flows. And rearrangeably non-blocking is that sometimes if you add more flows, then you really need to recompute flows that already are in the network. You need to recompute them and reroute them in order to overall provide that non-blockiness. So InfiniBand networks today are working in a rearrangeably non-blocking fashion. And basically, for all practical purpose, when you have collective operations which heavily use the network bandwidth, then there are well-known patterns. And the default routing for those patterns are usually computed by the subnet manager and are really optimized for those kind of traffic patterns so that they will not see congestion. But if you look about randomized flows and other characteristics of collectives that are unknown a priori, then you may suffer from congestion even if you have a full bisectional bandwidth in the network. So in this example, we have a red flow and a blue flow, and they happen to go to the same switch, and they happen to even share the same link. This is because the routing algorithm chose to put them on that link. So obviously, there is enough bandwidth in the network to route them through different links and different switches, but the subnet manager, when it did its calculation, put them on the same link. So this is where adaptive routing comes into play. So for doing adaptive routing, or as we call here, traffic-aware load balancing systems, there are two approaches to how one could achieve that. So one approach is centralized adaptive routing, and the second approach is distributed adaptive routing. So let's talk a little bit about the centralized adaptive routing. So the concept is shown here on the left-hand side. Basically, let's say that we have a flow, a red flow that wants to fly into the network. Basically, before that flow goes into the network, it will get admitted through the central routing control. So basically, each time you want to start a flow, you'll have to go and consult with that centralized entity that will have the full picture of the network, will be aware of all the flows, and will make sure that the routing is programmed the way it will enable non-blockiness in the network. This is assuming that we're talking about permutation of pairs and not oversubscribed by design. So the scalability for such approach is extremely low, right? We're talking about huge networks, and we're talking about a centralized routing control that needs to be aware of all the flows in the network and all the switches and all the links. So that's something that is definitely not scalable. The knowledge is very good because it's global, so you can do optimizations that are globally on the network, and it can provide really non-blockiness. I would argue just one thing here, because when you say non-blocking, then there is some level of blockiness here, because when a flow wants to start, it has to first go to the centralized unit, centralized manager, and ask for a permission and ask for the route, and that thing can take time. So there is some blockiness when you want to initiate a flow, and there is some also question about what happens when a flow stops, and you also have to register yourself to unregister that flow from the network. So let's talk a little bit about the distribution adaptive routing, and that's actually the approach we're taking on adaptive routing. So first of all, anything you do distributedly is higher scalability. So that's one thing. So the knowledge is obviously local. So every switching decision will be able to do a self-routing. So every switching element will have control of what traffic goes through which links. And the non-blocking is a little bit unknown, but we'll show you a little bit about how it works. So it's kind of a converging algorithm that's supposed to go into a state where all the flows can go through. So if you look at the self-routing unit, if you see those two flows, this red flow and the blue flows, they will go through those first switch, and that first switch will pick up one of the possible links. So in this example, all those spine switches are allowed to go. So that switch will pick up to go to that spine, and that switch will pick the blue flow to go to the other spine. And then again, the next tier will choose whatever next leaf it will go through, and that's how the flow are selected. So in this example, each routing element pick up the right path so that there is obviously no contention between the blue and the red flows. So basically, this is the distributed algorithm for doing adaptive routing. It's somewhat more limited but more scalable, and this is the approach that we're taking for adaptive routing, and I'll show you also a little bit about how we further optimize that approach. So let's look at an example, okay, because it's always easy to see in an example how things converge into the right optimal routing. So let's look here at the three flows, the red, the blue, and the green that want to arrive to that destination. So potentially they can go nicely within the network, or they can create any congestion or contention, which you need to be alleviated by the adaptive routing. So what happens is that first trial here, all those switches will randomize their output ports. So let's see. This one picked up this port, that port, and this other port, and the traffic will go through those ports. So what happened here is that there became a congestion between the green and the red route, the green and the red flows, because they happen to go through the same link here. So basically, each one of them will get half the bandwidth, and congestion really happens here. But that's not a true congestion, because if we want, we can reroute and fix that problem. So what happened is that this switch will realize that there is a congestion that happens and will reroute the red flow through a different path. So it will randomize again a different port and it will route through that switch. So again, that was also a wrong decision to do, but again, congestion will happen. And in this case, the blue one decided to back off and move the flow to a different switch. And last, the flow get through disjoint switches and disjoint links and everything really converges. So again, the adaptive routing is a reactive mechanism. It takes a little bit time to converge, but it's very scalable and taking a decision on a hop-by-hop basis. So making each switch a little bit more smart, having the subnet manager program the different path there, the different alternatives, and taking a decision. It's a hop-by-hop thing. Yes?
So, how much penalty or time that will take for this operation? Because it's possible that the decided to go to the first one, it might go also the green one.
Right.
Because it doesn't know about what was going on between the red and the green.
Right, so the question was about the time it takes those things to converge, and indeed this is one of the parameters that we're tuning and optimizing. So first of all, you need to, experience some kind of congestion to understand that you really want to switch paths. So this is one characteristic of how long it takes you to react, and that's something I'll show you in the next slide how we can improve. And the other thing is the number of trial and errors that you need to do in order to converge to that path. So first of all, this optimization is heavily tuned for longer flows, because very short flows, you don't need these conversions because there's enough buffering in the switches, to kind of buffer everything and propagate things. So that's fine. So this is mainly intended for long flows and fixing the routing there. And we're still working on optimizing and making sure it converges faster in time. But that's indeed a good thing, a good point. One of the things that give this mechanism longer time to converge is the detection of congestion. So what basically happens, if you want to look at this example when it started, so when we had this congestion between those flows, what happens here is that this switch buffer will start filling up because it gets filled in a twice data rate than it is able to send out. So when those buffers fill up, then only then this switch will see that there is congestion and will need to reroute that flow. So those things take a little bit time to converge, and this is one of the things we're optimizing in a new mechanism called ARN. So let's talk a little bit about ARN. ARN stands for Adaptive Routing Notification, and it's a mechanism that optimizes the local decision that takes place in a switching unit. So basically you can see in this example that there is a purple flow and an orange flow. Let's assume that they're not high bandwidth flows, and they're happily living together. They happily live together and they're not creating any congestion. Now let's see that we want to inject a new flow, a new red flow that will go through those switches, but this is a heavy flow, and that flow is going to create a congestion. So basically what will happen now is, if we go through the mechanism that we described before, it's going to take a while until this switch buffer will fill up, and then that switch buffers will fill up, and then only then that switch will will realize that there is a congestion in place and will try to reroute that red flow. So instead what we're doing here is that we're doing some kind of sampling here in that switch and identify that there is a congestion, because that's the first place we know that there is a congestion, because we're seeing 3 flows going into one destination port, and we're seeing that the congestion starts to build up. So, and we're doing a little bit of sampling so that there is more likelihood for the flows that are more heavily used to be marked as candidate for rerouting. And then we send a special message called ARN, the Adaptive Routing Notification, back on the path of the packet. So that ARN will go back, and actually in this switch there is nothing you can do, because the red one comes in and have to go out from that port, so there is nothing that switch can do. So this switch will further send that ARN back another hop, and this switch can actually do something nice about the red flow. It can actually move it to a different port. And what happens is that this switch will identify the ARN, will see that there is a congestion piling up, and it will reroute the red flow through that other stuff. So I didn't show the entire network, but let's assume that this path is valid, and that's one thing that the adaptive routing can do. With this mechanism, it really is improving the overall time it takes the system to converge, because it identifies congestion ahead of time and doesn't need to propagate all the buffer filling up in the different switches. Yes?
So will head of line blocking not kind of destroy the effectivity of the sampling?
So basically what happens is that if you look at head of the line blocking, first of all, we're talking about different flows. So always they're buffering for flows coming from different ports.
Let's say they go to the same output port.
And if they go to the same output port, so you identify flow by sampling. So usually the fast flow will have more real estate in the buffers than the slow flow. And that's the idea of sampling. But in either case, you're going to mark and send backward notification. So even if you mark some other flow, the network will try to reroute those other flows. So it's a matter of converging the algorithm by trial and error, moving things around until things converge, or it might be steady state of moving things around. Yes?
Yeah, so just wondering, so this would be reaction as effective?
So
you basically said about the explicit backport.
Okay, so the question was about comparing this mechanism to fecend and backend mechanisms, right? So first of all, fecend and backend, they're somewhat similar because they go there is a backend that goes back in the network, but they're handled in different layer by different devices. So fecend and backend, they're created. Fecend is marked by the switch, but it will be handled at the layer 4 by the adapter. So backend will be sent by the end node adapter, and the backend that will come to the transmitting node will be served there by the transport layer by reducing the injection rate. Here, this is all handled by the switches, and the result of this thing is not reducing the injection rate, but actually changing the route. So they operate at a completely different layer, and I think that those two mechanisms are somewhat complementary. Because congestion, because in this case, or even in the previous slide, there is no real congestion because the network can actually let all that flows coexist. It's just a matter of routing that wasn't optimal. In the case of congestion management, it's usually used for the cases of incast or many-to-one, where the network, regardless of the routing, cannot really tolerate that many flows that come through the network.
Sure, but,
Yes?
But the triggering in the switch is the same. You notice you removed of the congestion tree, and that triggers the switch.
Right. The triggering for realizing congestion is very similar between ARN and marking for fecend. That I agree. All right. So here are some numbers comparing the Mellanox adaptive routing. Those things were measured on InfiniBand FDR system versus Cray arrays. So you can see here different cluster sizes, anywhere from 16 node to 15 or 1600 nodes. And you can see, unfortunately, I don't have all the data points, but you can clearly see that InfiniBand FDR with adaptive routing scales better on a B-effective benchmark. So this benchmark actually is doing ordered and random rings of data, and is moving data in both directions of the ring. And it's basically, I think, using a single process per node here just to stress the interconnect and try to move as much data in fully randomized pairs of nodes. So that really puts it very hard on a static routing computation. So you can see here that obviously with the adaptive routing, the FDR is actually performing better than alternative interconnect that is also using other mechanism of adaptive routing. Yes?
What's the topology here, right?
The topology here, I think, for the FDR InfiniBand is a fat tree. For the areas, if I'm not correct, it's a dragonfly, so it's slightly. I'm not sure. I need to check the data. But both of them are using adaptive routing to optimize the performance. Yeah, I have some more data about this, but I didn't put it in the presentation. But we can clearly see that in Factory, for this specific benchmark, that we're seeing better performance when you turn on adaptive routing, especially when cluster size grows, because it kind of randomized the pairs or the permutation and give it really hard time on static routing to actually match the bandwidth. Yes?
Is it possible to prioritize traffic?
Possible to prioritize traffic? Can you give an example?
I mean,
By service level or? Yeah. So this was a very. Yeah. So it's possible. Yeah. Okay. So let me go through it. So I just give a brief introduction about adaptive routing, but basically it's heavily configurable. So you can choose to do adaptive routing on different traffic based on the traffic class or based on marking done at the host level. So there is a lot of flexibility on when to do adaptive routing, and there is also a lot of flexibility of how to do adaptive routing. The principles are this, but you can obviously choose which kind of adaptive routing you want to do. So there is a lot of options there for tuning. Yes?
Do you have any numbers for the FDR on the 28?
No, unfortunately, I don't have those. Unfortunately, I don't have those data points. I have some other data points I didn't put in, just showing on between InfiniBand and itself without adaptive routing and with adaptive routing, and we see that the moment the cluster scales beyond a single switch, you can see the optimization. But I don't have this. I unfortunately don't have those data points for FDR yet.
And here you can measure only bandwidth, but do you have anything else like latency, like with this benchmark tool?
Yeah, I don't have. This is what we actually have, and this is very popular inquiry that people are doing when building a cluster. They pretty much look at this metrics, but I don't have further data. The more installations we have, I'm sure that within the coming year we'll have more and more data, and that could be part of HPC Advisory Council to collect those data and see the benefits there. Yes?
Can you update the software of the current FDR switches with static routing so you can gain the adaptive routing?
I don't have it from the top of my head, the software stuff, but we can definitely follow up afterwards, take it offline. Yes?
what is the actual setup that you have with 1,500 nodes? What is the topology? Are you only using one switch?
No, 1,500 nodes is definitely multi-switch topology, and those were actually measured on a system.
How do you compare this? How do I interpret this?
The bandwidth is described on the x-axis, on the y-axis here, so it's in megabyte per second. That's the numbers that are retrieved from the benchmark.
On every port.
Yeah, I believe that it's average or something. I can follow up on this later. I don't have the exact details.
The hopes that, let's say that the traffic goes through the topology that has to go through the same.
So the topology, as far as I know, on the blue lines is fat tree topology. So it's basically running a subset of the same cluster on a fat tree, and the red ones are usually run with some other topology with Dragonfly, obviously on subsets of the cluster. Yes. One last question on the adaptive routing.
Do you have any data for more than 1,500 nodes?
Currently we don't have, but I'm sure that over the coming year we'll have more and more data on adaptive routing, and we'll gladly share that, either through the HPC Advisory Council or through other mechanism.
What do you expect?
So we expect adaptive routing to enable better scaling. As I mentioned, there are some challenges because of the local decision, which is obviously optimized by the ARN, but it's yet to see and measure. But those are, high-level stuff that we have. Those are the principles, and with that we intend to scale into larger clusters. All right. Yeah.
Will this require changes to the
So again, this is something that is a pre-standard phase. This is something that we have mechanisms to program the switches and the adapters. Later on, this could be contributed into the InfiniBand spec to enhance that. So until now, we have a track record of opening many of the features and standardizing them through the InfiniBand Trade Association. All right. So let's move a little bit to HPC and continue. I think let's leave the other question to the end because in the interest of time, so I'll try to show you a little bit more about other technology and advancements that we have for HPC software. So HPCX is a full package for HPC middleware that Mellanox provides. It's a fully tested and packaged suite that includes MPI, PGAS, and OpenSHMEM, and UPC. It's fully optimized for Mellanox InfiniBand adapters and third parties. It maximizes the application performance. I'll show you a couple of graphs showing the application benefits from HPCX. It's fully tested, it's supported and packaged, and it's available for commercial and open source usage. So the way it looks is that you can run your HPC application unmodified. Everything can run on top of HPCX, and HPCX includes all the components that we mentioned, including MXM and FCA. Basically, those two components enable the point-to-point. This is based by MXM, and obviously, we also have collective offloads mechanism that is delivered by FCA. Everything runs on top of standard Mellanox OFED. This is the interface is the OFED verbs. So basically, technologies that are available from Mellanox OFED or the HPCX takes advantage of those technologies like Peer Direct, Core Direct, GPU Direct, and so on. They can run on the operating system, and they support different interconnect technology, anywhere from Rocky through InfiniBand in third-party interconnect. And we support different platforms, as I mentioned before, different compute platforms from x86, Power8, ARM, as well as GPU, and later on we'll have also FPGA. So that's a full comprehensive software suite. And we can see a few examples of performance. This is one example of fluid dynamics where you kind of scale with the cluster size. This is the number of nodes on the x-axis. You can see anywhere from 1 to 96 nodes. And basically what we're showing here is that compared to Cray, the performance you're getting in 32 nodes is high enough here that you don't have to go into 96 nodes. You can just get away with third of the size of the cluster for getting the same work done. So this is why we stopped measuring at 32 nodes, because the overall maxed out the overall performance that you can obtain at 96 with other interconnect. Other example from fluid dynamic and computational molecular dynamic, again, 58 performance advantage. This is for HPCX versus OpenMPI. This is due to MXM integration and FCA. Another is 21 performance advantage compared to PMPI and Intel MPI. And another 20% performance advantage between OpenMPI versus HPCX. All right, so that was a brief introduction about HPCX, and I want to talk a little bit about GPU Direct RDMA and the next things that will come to further extend the GPU Direct concept. All right, so Peer Direct you're pretty much aware of, and this is a technology that has evolved over the years and enabled better connectivity for GPU. But this technology goes a little bit beyond GPU. That's why we call it Peer Direct, because it really enables a peer-to-peer communication through the PCI bus, and it can be used not only by GPUs, but also by other devices. It can be FPGA, it can be SSD device, and any other device that has connectivity. So basically the architecture is pretty much open. Any adapter, any PCI device that want to support peer-to-peer needs to implement some kind of a software plugin that enables mutual memory registration, sharing with the HCA, and that will pretty much enable the connectivity. So basically, we're talking about a system where you have a CPU with its memory, a GPU, or any other accelerator with its memory. They're hooked together on the PCI, and there's the RDMA adapter. And basically, instead of the traffic going through the adapter, through the system memory, and then copied through the GPU memory, you can go directly from the adapter through the GPU memory or through the accelerator memory directly. So this example is the GPU Direct. We label it as GPU Direct 3.0. This is the third generation. It pretty much shows in the slides that you can get directly from GPU memory. You can read the data using the HCA through the PCI Express and put that into the GPU memory on the other side without any CPU involvement in copying the data between CPU memory and GPU memory, and even without triggering anything on the data path here. So it's, first of all, very efficient and reduces latency, solves bottleneck, and beyond that, it's very efficient in this computation. A few examples that were shown even in that were shown by Ohio State University, by DK Panda, is 67% decrease in latency running GPU Direct compared to running a non-GPU Direct version, and 5 times faster in larger message size bandwidth using GPU Direct because you don't need to copy the data by the CPU. And real application performance measured with GPU Direct is the HUMD. It's a performance, and you can see that the larger the cluster is, the larger the benefit is from using GPU Direct. You can see about 2 times faster in 96 node, better performance running GPU Direct RDMA. So what's coming next on the GPU Direct, okay? Because those are old news, and the next thing that is coming on the GPU Direct is an ability to not only do the data path on the GPU, but also do the control path on the GPU. So today with GPU Direct 3.0, what you're able to do is to tell the HCA to move the data to and from the GPU memory, but still CPU has to turn on, to submit the kernel to run on the GPU. It needs to wait for the kernel to finish, and then it will trigger the HCA to send the data. So the CPU is heavily involved in the data path, and also there is latency involved in the CPU to wait for the GPU to finish the kernel, and then submit the job to the HCA to send it and then move to the next computational phase. So what we basically are planning to do with GPU Direct 4.0 is to have the control path also being done by the GPU. So for example, the CPU can give a kernel to the GPU to execute, and then tell the GPU whenever that kernel is done, then the GPU can also fire the transmission of the communication to the next node without having the CPU waiting for it. So all the control operation will be able to go and be executed directly by the GPU. So this pretty much saves a lot of latency between the GPU finishing the job to sending it to the next node, and also is way more effective than the way it is implemented today, where the CPU actually blocks waiting on the GPU to complete. So some examples, and those are very, very preliminary experiments of peer-sync technology. You can see about 27 or 23% faster on a 2D stencil operation. Those numbers were measured with the peer-sync operation on 2 and 4 nodes. So this is all very new, and we plan to continue working on that and bring more and more technology and innovation into the GPU Direct. And another nice technology about GPU, and that also take us in the discussion more into clouded environment and shared resources. So sometimes the GPU is enough in providing all the capability that the server wants, but sometimes you don't need a full GPU for a server, and this is something that you can really use the RDMA technology in order to provide remote GPU access, so you can kind of virtualize the GPU service in a clouded environment or in a shared environment, so you can virtualize that GPU and move data very efficiently to the GPU. So that technology is really enabled by RDMA, and you're able to kind of get performance of the GPU very, very similar to a remote GPU. So basically, there is a very little and very negligible overhead when you're sharing a GPU compared to having it locally. And once you can share it, then you don't need to buy as many GPUs as your compute node. You just buy and scale the number of GPUs independently according to the numbers that you need. The next thing that comes into data center is the multi-host technology. And I'm really excited to mention that we kind of announced this technology I think 2 weeks ago in Open Compute conference. So what's happening at the data center is that, we have many servers and then multi-cores, but the next thing that is going to come is a multi-host design. And this is a capability to run multiple CPUs and share the same NIC across those different CPUs. So this is a very new technology, and it will enable different form factor and different building blocks of the data centers that are more economical and more scalable. So let's look at how server is built today. The server is typically a CPU with its memory and all its peripherals and connected to a single NIC card that usually comes on a slot or a London motherboard. And then the next generation is actually going to place the NIC and the server as modular selection, and you can connect multiple CPUs with a similar shared NIC that will split the traffic between the different CPUs. And that's the future of the data center design because it's enabled more scalability and it can basically save you the amount of links going on to the switch. So if you look at this example of a single server, single NIC per server, every server will require a NIC that has one connectivity that goes into a switch. And in this new design, you can share multiple CPUs or multiple servers that are logically connected here and use just one switch port. And basically, the scaling of the first tier will be done inside the shared NIC. So that connectivity actually enables lower OPEX and CAPEX when you're building the system. So basically, we're looking at this technology to enable connectivity of, let's say, weaker CPU like the ARM, for example, that they don't need the full 100 gigabit per second because they are weaker a little bit, and they can definitely use a quarter of the 100 gig link, and you can actually connect 4 ARM CPU directly and share the same NIC together. So that's a nice technology. And actually this platform, which is called Yosemite, that's an OCP platform. It was announced by Facebook. It's a joint work we did with them to design the platform. So basically there are 4 compute slots that each one is a logical server, and they're all sharing the same NIC card that is placed here. It's based on the Kinetics 4 multi-host capability. Yes? Yeah, CPU to CPU traffic all goes into the NIC, all go and process inside the NIC. So in terms of the model that each CPU is seeing, is each CPU believes it has its own dedicated NIC, and the traffic that goes through that card is basically an emulation of 4 different NICs. Each one goes to its own server, and a logical switch that switches traffic between servers. So only the traffic that needs to go outside will go through that link. Okay, and the experience from the host, it's not a PCI Express switching, it's a true networking ecosystem here that each server behaves. So each one of the server doesn't need to change any of the software model. It's the same software, same InfiniBand verbs or Rocky verbs, and same networking model.
Still, it has to enable itself on the PCI Express.
Right, so it has 4 different PCI Express bus. So the by 16 PCI breaks into 4 separate by 4 buses, and each server gets its own portion. So some people, after seeing that, will probably ask themselves, what is it? what's in it for me for HPC, where every server really needs the 100 gigabit per second bandwidth? So the answer is very interesting. So first of all, there are HPC that are using the ARM technology, and when the CPU is weaker, then sometimes you really want to take advantage of the 100 gigabit interconnect and be able to scale, but then, you know, each ARM server can get a quarter of the bandwidth available. The other interesting thing is how you can build a server that will be more efficient with the interconnect. So today we're seeing limitation of the NUMA interchip interconnect between the CPUs. So usually what we're seeing is that in a NUMA systems, the traffic here that goes between the NIC and the CPU the CPU socket that the NIC is attached to is more efficient than the traffic into the other socket. So basically what you can do is the multi-host technology, you can use the same NIC and connect that into two different CPUs with or without the QPI, and being able to have adjacency into those two CPUs together at the same time. So basically you can see here a few examples. I mean, the example here are pretty much obvious. Today, for example, on GPU Direct, you have to connect you have to connect the NIC to the CPU that has the GPU attached. Otherwise, you do not have peer-to-peer. So in this example, only the GPU Direct will work on that socket only. And that socket will not support GPU Direct because the NIC is not connected to that socket. And in this example, you can actually split the by 16 into 2 by 8 and enjoy with or without the QPI, you can enjoy GPU Direct on both sockets. So you can load that CPU with 2 GPUs and enjoy GPU Direct on both sockets. And another thing is also the overall performance, where traffic arrives to that CPU directly and you don't have the NUMA effect. So usually when you kind of run the same job on the same CPU, you can get all of that. In the interest of time, I'll just mention that, you know, with InfiniBand, you can also build InfiniBand Cloud, and OpenStack was mentioned here, so that's one of the stacks that we support for InfiniBand to run OpenStack InfiniBand Cloud, so you can manage InfiniBand Clouds using this. As well as we recently, last week, we announced cloud support with containers. So there is also RDMA available for containers, as well as in SRIOV. And to summarize, I have 2 slides. One important element for scaling into the next generation beyond 100 gig is the PCI Express Gen 4. That's the new generation that will double the performance available from the PCI Express Gen 3. And will add more capability, except in addition to the feeds and speeds, cache coherency, atomic operation, power management, and more. And just to summarize, we have a full solution for scalable high-performance computing, support of the different CPU and accelerator cards. Everything is standard-based with a full ecosystem and backward and forward compatible. The new era of 100 gig is starting now when we have higher performance adapters that scale. And we have a software stack, the HPCX, that is fully tested and certified and supported. That's all. Thank you very much. And I think we will not have time for questions because we ran out of time, but feel free to stop me outside and we can continue the discussions.